Hello, this is another highlight for a lecture in the introduction section to the fluid mechanics course that I'm teaching. And this one is about classification of the flows. So if you open up a CFD, computational fluid dynamics text, for example, you often see references to classifying flows into elliptic, hyperbolic, or parabolic. This is not what we're talking about. This is one important message. We are going to be talking about classifying flows based on the physical features. Why do we talk about classification of the flows? Well, this is an analytical approach that we are discussing, and we talked about that in analytical approach we're dealing with equations that represents conservation laws, conservations of mass, momentum, and energy. These equations are partial differential equations that in general form cannot be solved. The solution doesn't exist. But in specific cases, solution does exist, and that requires simplification of the governing equations. In a nutshell, it's dropping out or ignoring certain terms or parts of the equation and finding the solution of a simplified one. And how we go about dropping out terms or parts of the equation is by classifying the flow that that equation is describing. So making an a priori assumptions about what solution is going to look like. And the classifications that we're going to talk about are physical features of the solution. We assume that the flow is going to behave like this. It's steady or unsteady flows, viscous or inviscid, one-dimensional, two-dimensional, three-dimensional, external or internal, or laminar or turbulent. These are the main things, and our job as engineers or scientists is to basically make a call when it is appropriate to employ certain classification, to basically say, okay, this flow is 3D or this flow is steady, etc. The terms in the equations that are going to be ignored, they represent actual physical properties of the flow of the solution. So when we ignore some of the terms, when we simplify the equation, we're actually deciding that some of those physical aspects are less important than others, and that's the hard part, deciding which ones to keep, which ones to drop. So let's talk about some of these classes. The steady and unsteady I'm not going to even talk about here in this video. It's kind of obvious whether the solution is time dependent or not. Two-dimensional versus three-dimensional flows. It's good to make a simplification towards the lower dimensionality if possible, simply because there are fewer equations to solve. But there are some additional desirable features of simplified equations. I'll give one example. If you consider flow over circular cylinder, so circular cylinder in a uniform cross flow, the wake of the cylinder forms a well-known pattern of vortices that are shed. It's von Karman vortex street, and that pattern is what we call a quasi 2D flow. So even if the cylinder is very long, then there are not many changes in the out of plane direction. So the main changes in the velocity field occur in the 2D plane. So we can just consider a cross section of that cylinder and for all practical purposes predict the entire flow. But let's say on the surface of that cylinder we put helical strakes. These are kind of bumps on the surface that are wound helically around the cylinder. Let's say it's a wire that we wind over the cylinder. Then the location at which the flow breaks off from the surface of the cylinder will vary along the span, and the wake is going to be completely three-dimensional. So that by the way, that helical winding is a common feature for mitigating flow-induced vibrations. Each vortex, as it's shed, results in reacting force on the cylinder itself, and it vibrates. But if that shedding of vortices occurs at different phase along the span, then these forces, instantaneous forces, counteract each other. Well, there is an expanse of an overall drag increase, but the vibrations are reduced. And you can see examples of these helical windings on the car antennas or chimney stacks of power plants, things like that. So one of the main classifications that's the focus of this course is the viscous versus inviscid assumption. And as the name implies, for an inviscid flow, we assume that viscosity doesn't play a role. The interesting thing is that for a given flow configuration, some parts of the flow field can be assumed to be inviscid, and in some areas we have to take viscosity into account. So for example, if there is a flow over an airfoil and we draw a streamline pattern, then it's largely, the flow field is largely inviscid if the angle of attack is moderate. But if we look close to the surface of the foil, we observe so-called boundary layer. This is where the viscosity slows down the moving fluid particles. So at the surface itself, the fluid particle cannot move. It's stuck to the surface, no slip boundary condition. And then that fluid particle, because it interacts with the neighboring particles through viscosity, it slows down the particle next to it, and that slows down the next, and so forth. And that forms this boundary layer velocity profile. It manifests a deficit in momentum. So and if we integrate it over the surface, we get the drag force on the body that's immersed in the flow. So there is a region very close to the surface where the flow is viscous, and it is inviscid otherwise. What is special about inviscid flows is that inviscid flows are irrotational, so vorticity is equal to 0. So vorticity is the measure of rotation of a fluid element. The reason for that is intuitively, very in simplistic terms, can be explained like this. Let's say we have a cubical fluid element, or in 2D a square fluid element. It experiences various forces from the surrounding fluid. Those forces can be broadly classified as body forces that act on the entire fluid element, such as gravity, and surface forces that act on the surface. In turn, the surface forces are classified into the normal forces, which is pressure, and tangent forces that act along the surface, and these are the shear stresses. And it can be shown experimentally that for so-called Newtonian fluids, the shear stress is proportionate to the strain rate of the fluid, and it's related to derivatives of the velocity. In the simple case, boundary layers, pipe flows, the shear stress is proportionate to the velocity gradient in the normal direction, and the proportionality coefficient is the physical property, it's the viscosity. Now, consider that fluid element again. If the fluid element was flowing through the stream without any rotation, then the body force, if we apply the body force, it just translates the entire thing. It doesn't, cannot impose rotation on the element. Likewise, the pressure. Pressure acts normal to the surface. It can compress or expand it, but no rotation is possible. The only way to impose rotation on that fluid element is to apply a shear stress to it, and the shear stress, as we just saw, is related to viscosity. So that is the main premise and the consequences of that classification into viscous, inviscid, or in turn rotational or irrotational flow classification. How that manifests itself in the transport equations, this is what we're going to consider. We can also talk about internal versus external flows. Classification itself is straightforward. You just, if it's a pipe flow, it's obviously an internal one, but just like the external flow over the airfoil, if you consider a flow in a duct, for example, you can see the regions where an inviscid or viscous assumption can be made. So for example, at the entrance to the pipe, in the region near the center line, the flow is initially irrotational and inviscid, and the boundary layers grow on the walls, and as the viscosity affects more and more fluid particles away from the walls, eventually the boundary layers merge and the entire flow becomes viscous. By the way, some distance from the entrance, the flow becomes fully developed, so there are no changes of any parameters in the x direction. That's an important condition that can also be used to simplify the governing equations. The laminar or turbulent flow classification, it's a challenge. The primary challenge is in predicting the details of the turbulent flow, but actually classifying the flows into laminar or turbulent, the distinction itself is not very difficult. We have intuitive understanding whether the flow is laminar or turbulent. For example, if we consider a laminar boundary layer, so flow over a flat plate, let's say it's water, and we add a dye marker, the tracer, to the flow and take a video or a photograph, so it's a flow visualization experiment, we will see that the dye tracer will just move smoothly and trace some trajectory that's fairly predictable, certainly regular. In contrast, if we consider a turbulent flow, we can see that the same dye tracer will undergo a very highly 3D unsteady trajectory. The dye will mix very rapidly in the flow, so these are characteristics of a turbulent flow. The more formal definition is quite a bit more elusive. One thing we can say that the turbulent flow is necessarily unsteady, it's 3D. The flow parameters such as velocity components and pressure, they fluctuate. So the flow has vortices or eddies. It's composed of these vortices. They are oriented in the 3 dimensions, and there is a large range of scales of those vortices. In the case of the boundary layer, for example, the eddies range from the size of the boundary layer thickness itself all the way to the microscale, so-called Kolmogorov microscales, where the viscothermal dissipation happens, where the kinetic energy of the flow is dissipated as heat due to friction or viscosity. So all these scales are present, which makes predicting the details of the velocity profile quite difficult if the flow is turbulent. What makes it also difficult that even if we're interested only in the time averaged characteristics of the flow, for example, the time averaged velocity profile of a turbulent boundary layer, that shape is influenced by the small scale fluctuations, so these high frequency vortices that exist. So we are compelled to study those to gain some insight into the motion of the smallest stages in order to predict the large-scale details. And this is when the turbulence is the unresolved challenge in fluid mechanics. So it's a very difficult problem to consider. So definitely it makes sense to make a distinction a priori on whether the flow is laminar or turbulent. If it is laminar, this simplifies things considerably. If it is turbulent, also it kind of steers us into the direction of the methods that are suitable for those turbulent flows. So that's all we're going to consider here. So we at this point we're not going into the details, but just generally consider that in order to simplify the set of the governing equations of a very general fluid mechanics problems, we need to make it less general. We have to be more specific. We could say whether it's steady or unsteady, two-dimensional or three-dimensional, laminar, turbulent, internal or external, and which would be the focus of this course is the viscous or inviscid. So that's what we are considering here, and we'll talk more about this next time.